decision tree is like a flowchart. They break complex decisions into smaller, easier ones, just like we do in real life. They're used in supervised learning to solve classification and regression problems. Let's see how decision trees can be used to make smart predictions in healthcare, like identifying if a patient might be at risk based on their symptoms and test results. Let's begin by importing the necessary libraries for our decision tree. We'll need Pandas for data manipulation, NumPy for numerical operations, Matplotlib for visualization, and several modules from Sklearn for our decision trees and metrics. Now we'll load our diabetes prediction dataset. The data will be downloaded from Kaggle and unzipped automatically. So let's examine the first few rows of our dataset to understand its structure. Here we see several features that might be predictive of diabetes, including age, BMI, blood glucose level, and hypertension status. The target variable is diabetes, which indicates whether a person has diabetes or not. Let's get a little more info about our dataset. So this information gives us a better understanding of our dataset structure. We can see the number of entries, data types, and get a statistical summary of the numerical features. Now we'll prepare our data for modeling. First, we'll separate our features x from our target variable y. For simplicity, in this demonstration, we're dropping the categorical columns gender and smoking history to avoid encoding them. In a real-world scenario, you'd want to properly encode these features. We can confirm that the shapes of our feature and target arrays match what we'd expect. Before building our model, we'll split our data into training and testing sets. The training set will be used to build the model, while the testing set will help us evaluate its performance. We're using a 70-30 split with 70% of the data for training and 30% for testing. The random state parameter ensures reproducibility of our results. We can also check the shapes of our resulting data sets to confirm the split worked as expected. Now we're ready to build and train our decision tree classifier. We'll start by initializing the model with a random state for reproducibility. Training the model is simple. We'll just call the fit method with our training data. The model has now learned the patterns in our diabetes dataset. We can also adjust the hyperparameters to control tree complexity. Here, we're setting a max depth of 5 to prevent the tree from becoming too complex, which helps avoid overfitting. This creates a balance between model accuracy and generalizability. One of the most powerful aspects of decision trees is their interpretability. So let's visualize our trained model to understand how it makes decisions. Each node represents a decision based on a feature value, with branches showing the different outcomes. Leaf nodes show the final predictions. The color intensity indicates the proportion of samples in each class. This is a pretty busy visualization. For clearer visualization, let's look at a simpler version of the tree with a maximum depth of 3. This makes it easier to understand the most important decision rules that the model has learned. In this simplified tree, we can clearly see the most important features for diabetes prediction because these are the ones closest to the root. The algorithm has automatically identified the key thresholds that best separate diabetic from non-diabetic patients. So this concludes the first part of our decision trees demonstration, where we've covered the basics of decision trees and built our initial model. In the next part, we'll evaluate our model's performance and learn techniques to avoid overfitting.